Next, we have to see the definition equivalence relation. The relation R is defined from A to B. A relation R is defined from A to B is said to be equivalence if it is satisfying reflective and symmetric and transitive. The R is said to be equivalence relation if it is satisfying reflexive, symmetric, transitive. R is satisfying three relations. For example, I be a set of integers, then I cross I, which is equal to a comma b. A comma b belongs to integers I. R is related relation. Let R equal to a comma b order pair a comma b such that a comma b belongs to I. A less than b is the multiple of fixed integer n. So R is relation defined on I. Verify R is equivalence relation defined on I. This is the problem. Let R equal to order pair a comma b. So a less than b is the multiple of a comma b is the multiple of fixed integer n. So we have to prove R is relation. It would be equivalence relation. So first let us taking a comma b, a comma a, two element in capital I set of integers. So a minus b is equal to a minus a equal to 0. Multiples of n is the multiples of n. So a relation a is related to a, R is reflective. Then next we have to prove R is symmetric. So a comma b is two integer in set of integer I. Suppose that a is relation to b means a minus b is the multiples of n. So b minus a is also a multiples of n. So b is related to a. Therefore R is symmetric. We have to prove next. We have to prove a b c belongs to integer set of integer I. Suppose that a is related to b and b is related to c. I have to prove a is related to c. So a minus b and b minus c are the multiples of n. A minus b and b minus c are multiples of n. A minus b is the multiple of n. So a is related to c. Therefore R is reflective. Hence the above relation R is the equivalence relation. Next we have to see function or mappings. So function or mapping, that is one or more condition the function or mapping is satisfying one or more condition, then the relation is mapping. The relation is also called a function that satisfying one or more condition. It see the following. So let A and B any two non-empty set. A mapping from the set A into set B. A mapping from set A into set B is the rule which is associated with each element in set A is unique element in set B. That is, a function from set A to B a function from set A into B. Set B is rule associated with each element in set A use unique element in set B. A mapping or a function f from set A into B is denoted by f from A to B. Let f from A to B, A is called a domain and B is called codomain. Let f from A to B, therefore A is called domain of f and B is called codomain of f. Small b is the element in B which is assigned by A under the mapping f. It could be written as f of A equal to B. Therefore, f of A equal to B, A is called pre-image of B or inverse image of A is also written as f inverse B equal to A. Next, range of a mapping or function. Range of a mapping is a subset of codomain. So subset of codomain consisting these elements having relation with at least one of the element in domain A. The range of f is denoted by f of A, that is f of A equal to f of x, x belongs to A. For example for range is let A equal to 1 to B, B equal to 1 to 3 4. Therefore f from A to B is defined by f from A to B is defined by that is the example is A equal to 1 comma 2, B equal to 1 comma 2 comma 3 comma 4, f equal to A to B is defined as f of x equal to x square, that is f of 1 equal to 1, f of 2 equal to 4. So A be a set of books in library, let n be the set of natural numbers. These are the examples of domain and codomain. So next we have to see the definition of set of order pair. Definition on set of order pair. Let Sn be two non-empty set. A mapping defined from S into T is subset of denoted by S cross T, such that for all S belongs to S, there exists a unique T such that M is subset of S cross T. For example, S 1 comma 2